Hello and welcome. This video offers a brief overview of our senior design project at the University of Akron for spring 2024, focusing on the design and creation of a modular solar shingle solution. The team consists of Mitchell Cozzens, David Dye, Tyler Jones, and Andrew Schmidt. The accompanying pictures show our lab space.
Our modular solar shingle project was to design and prototype an affordable solar shingle that would be easy to manufacture and install. The goals were to print our circuit onto a 3D printed part and have easily interchangeable shingles.
For mechanical design concepts, we needed solutions for the problems we encountered during our iterative design process. These solutions include a box and case solar cell, built-in electrical connectors, a polycarbonate pane, an overhang along the two edges of the solar shingle, magnetic electrical connectors, and a gasket. For our design timeline, we started with sketches of different methods for encasing the solar cells and electronics. Then we sketched the first draft, modeled the first draft, created more sketches for a different electrical connector, and went through a couple more model iterations to land at our final design.
Among the many thermoplastics available for use, our team elected to use ASA, a polymer material made up of acrylonitrile, styrene, and acrylate monomers. This filament stands out due to its superior UV oxidation and weather resistance, which prevent the degradation of mechanical properties due to prolonged sun exposure. ASA also boasts inherent water resistance from its layer adhesion during printing. Temperature resistance is critical for the curing of the circuit, as similar filaments would experience severe warping from internal stresses. A printable circuit board, otherwise known as a PCB, was developed and modeled for the solar shingle. This approach was taken in lieu of using wires, as it could be used for batch manufacturing. The pads at the base of the circuit serve to connect the terminals of the solar cell, and the trace along the top to close the circuit when placed in line with other solar shingles. The solar cell leads were used in a pressure fit configuration, requiring only the electrical pogo connectors to be soldered. The open source program KiCad was used to create the PCB schematics, requiring dimensions and routings of the pads and 5mm traces. Once created, the fabrication layer was exported to a Gerber file, which would be processed by the Volterra Nova printer. The Volterra Nova extrudes a liquid semi-centerable silver conductor. This low resistance paste is what allows for the extruded circuit on the 3D printed base. After mounting the base of the shingle in the Volterra Nova, a probing tool measures the surface height every 2mm. This helps to correct for the surface roughness associated with the 3D printed parts. Once the Nova is finished extruding, the circuit and the shingle base was then moved to a heated bed to be cured for 17 minutes at 135 degrees Celsius. This time and temperature was selected to allow curing of the traces without warping of the shingle base.
Acetone vapor smoothing is a post-processing technique for ASA 3D printed parts. Acetone vapor acts as a solvent and removes layer lines, which can increase weather resistance and improve some strength properties of the material. The creation of a vapor smoothing chamber allows for an improved and better controlled process.
To aid in the design and testing phase, an Arduino power monitor was created and coded to eliminate the need for a multimeter. The system, comprised of an Arduino Uno R3, voltage and current sensor, and LCD display, allowed us to monitor the voltage, amperage, and effective power produced by either a single solar cell or an array. The code, alongside the serial monitoring program PuTTY, allows for daily trends of peak power to be graphed. In addition to the power monitor, a selection tool was developed in MATLAB, and consulting and contracting firms, it's necessary to be able to quickly determine how many solar shingles it would take to cover a roof. When a roof's width, length, and pitch are input into the program, it will output a graph of the simulated roof as well as the expected power output.
Our final prototype parts are capable of snapping together, creating a water-resistant layer covering the roof, all while generating electricity. Using ASA caused issues with 3D printing as well as curing the conductive ink of the circuit. Warping would occur in both processes. After using different printers and curing the circuit at different temperatures and durations, we were able to produce a winning process with little warping observed.
This project taught us the criticality of tolerances in modeling and in the variability of 3D prints, the effects on warping and print curing from temperature differences and rapid cooling, and the importance of planning with ample time for unexpected problems and a multitude of iterations. To create an environment for effective teamwork, we planned weekly meetings throughout both semesters, consistently messaged through Teams and text, created detailed meeting notes to document our action items in progress, and created a running task list with assigned team members and deadlines.
We are very grateful for the help and guidance of Dr. Kanan and Aaron Trexler over the past 2 semesters. And we would also like to thank Dr. Nadkarni and David Peters for approving our idea and supporting our efforts during this project.